thank Professor Son and the center for the invitation on this great event. I'm Dong Lee from Korea University, and so I just came from restroom. I thought there was a coffee break, and I especially thank Professor Choi. He gave a talk uh, in advance, so I really enjoy my role of the last talk. And since I'm the last speaker, I try to give as short as possible and as concise as possible. Okay. All right. So this is the image from the review paper we just submitted recently together with Professor Jae-hyung Kim. So basically in our lab, we uh, we only use diamond and B-center, but we cover from very fundamental methodology for advanced quantum sensing to the industrialization of quantum sensing. And among the various topics today, I'm going to focus on some imaging application, potentially applicable for studying, exploring quantum materials. Okay, so I think there's some echo. So I think Professor Dr. Chulgi Kim from KISS, he already gave a nice introduction about diamond and center. So I don't want to talk about it in detail, but among many other qubit platforms, I think the advantage of diamond and center is this slide. So diamond and center, which consists of nitrogen vacancy and carbon, nitrogen defects and carbon vacancy, it acts as a trapped ion, as Professor Choi discussed about interview one. But we don't need a vacuum or trapping laser or electric field. It's basically naturally trapped inside crystal lattice of ion. So if you, in terms of defect, it has many common property of trapped ions. So it operated as a qubit even at room temperature. But at the same time, the host material diamond is solid state material, so it can be fabricated and into the chip or scalable and so on. So this is the one of the advantage of diamond epicenter. If we fabricate diamond like scanning through microscope and positioning epicenter at the tip apex, then basically we can realize quantum sensing at with very high spatial resolution. So in that sense, I think this has a great advantage for searching for quantum materials. Just I want to briefly illustrate the advantage. It can detect many different physical quantity, but basically, it has high sensitivity for magnetic field, and spatial resolution is on the order of 10 nanometer, and it can operate from room temperature down to cryogenic temperatures, and it can detect from DC to AC up to gigahertz AC field. Okay, so today, basically, I want to focus on two imaging application, hopefully useful for studying quantum materials. One is scanning microscope type imaging technique. The other is wide field microscope type imaging technique. The main difference between these are spatial resolution. If I want to have a nanometer scale resolution, then use single epicenter combined with scanning probe type microscopy, and then image magnetic field or oscillating magnetic field from transport device. But the downside of this is very slow, and the imaging area is only several micrometer square. So if you want to image larger structure with much faster time, then you better go with this technique. This case, we use multiple MB center, so it's not scanning. Just shine them together and collect their signal using camera. So you can image over, let's say, millimeters square large area with second or minute of imaging time. In this case, micrometer square takes hour. So it's slow but has a high spatial resolution. Depending on your application, can use either of these imaging techniques or combine these. So this is the outline of my talk. I'm going to briefly talk about this single spin scanning magnetometry and then why quantum microscopy, and then potentially discuss some topics for collaboration between me and the center. Okay, so nanometer scale image. So I think this part you already heard from Dr. Kim, that is very similar as trap ion. So we shine laser and collect a fluorescent signal from epicenter. The difference in this technique is the bottom part. Now the epicenter is combined with atomic force microscope type imaging tool, and the sample under study, for instance, like a graphene or some magnetic sample, can be scanned in three-dimensional direction with the nanometer scale resolution. If you combine the, okay, this is image of our room temperature setup. Under objective lens, we have diameter and scanning state. You zoom in this area, this is the tuning fork type atomic force microscope, and you can see some transport device, it's optical image. If you zoom in closer, this optical image show all the wire which need to generate 3 gigahertz microwave to flip the qubit. And then these are some sample device we come to study, and this is the diamond with the single epicenter. If you zoom in here, you can see there's a single epicenter from fluorescence image, and that's the image of the scanning probe, diamond scanning probe.
How do you get this to?
So we have two different sources, one commercial one, and the other one is we collaborate with Professor Amy Jainch at UC Santa Barbara. So we fabricate some advanced proof by ourselves.
I see.
But
there's
this one is commercial. This is picture from commercial.
How expensive it is.
It's quite expensive.
How about
The cheapest one is $3,000 USD. The little bit advanced one is 5 or 6,000 USD. And it's easily, when you approach this tip to the sample,
It's very expensive.
student, almost everyone break several proof, scanning proof, because it's, yeah.
But the important part is at the end of the tip, usually there's a one or that there can be multiple.
There can be multiple MB. So when we buy this, you can select. So far in this talk, many people so far utilize a single epicenter, but recent trend is use multiple epicenter, entangle them, or use some correlation measurement. So there's some advantage using 2 or 3 epicenter, but here I want to focus on just a single epicenter. And so after fabrication, you have to select scanning probe with has only a single epicenter. That's why it's expensive. The fabrication is also takes cost, but also you have to, the yield is not so high, so that's why the commercial one is expensive. So in our community, people utilize the technique to study various different exotic materials. This is a 2D material, ferromagnetic material, and then the magnetism is changing from ferromagnetic to antiferromagnetic depending on number of layers, and basically they image magnetic field from the sample and then analyze the magnetization map. And also the similar work from my other group. And so this is not only powerful tool to study magnetic property of the sample, but also it can also study transport device. So when current flow, it generates alternating magnetic field around. By measuring the alternating magnetic field, you can reconstruct current density. So in this case, this is the graphene devices. And by measuring magnetic field, they can identify different transport dynamics. So I don't want to go detail, but just I want to point out that this technique can be used to study magnetic sample as well as current transport devices. I just want to give a couple examples that we recently do. We basically utilize magnetic voltage in a polymer sample. And once we carefully study, measure Rabi frequency of the magnetic vortex, we find that there's very strong enhancement in microwave field. So in this case, the vortex and anti-vortex can generate several order of magnitude stronger 3 gigahertz microwave. And spatial resolution is 10 nanometers. So basically the idea is utilizing vortex and anti-vortices, we can generate strong microwave field with 10 nanometer each spatial resolution. Okay. Because as Professor Choice mentioned that microwave hard to concentrate, that hard to generate a localized microwave field, but this can be used for that. And also this is a graphene transfer device. And once you flow current to the graphene device with a narrow channel, and as you can see, the current density is higher in this narrow channel, and this is expected magnetic field. So the different sign means microwave coming out and coming into the frame. Of course, the polarity will be reversed when the direction of current is reversed. So the idea is, can we measure magnetic? Can we reconstruct current density math from the magnetic field? And the answer is yes. And basically, this is our measured image, and then this is reconstructed current density, which agree well with the simulated current density. Okay, so recently we developed a technique to improve sensitivity, DC and AC field sensitivity. So the idea is following. This is just a test sample. We flow current through this wire, DC current, and then we're going to image DC magnetic field. And the quantum sensing methodology, usually AC sensing technique gives 10 or 100 times better sensitivity compared to DC protocol. So the idea is you oscillating MV center effectively convert DC magnetic field into AC magnetic field. Then we can apply this AC sensing protocol to our MV. In this way, so the signal itself is DC, but we can effectively convert that to the AC field. So this is a conventional static DC magnetic field, image of DC magnetic field, and this is the we call gradiometry method. And if you look at the cross section line code of the data, you can already see the improved SNR. And from the calculation, we expect compared to the conventional DC measurement technique, which have the 26 times improvement in sensitivity. We extend this idea to further. So this is the effectively convert DC signal to AC, but still we are measuring DC magnetic field. We like to extend this to the AC magnetic field. So we call AC gradiometry. I don't want to go detail. Basically, the signal itself AC, and we also oscillating our MD. So there's some mixing happen. Two different frequency we mix. So frequency can be added or subtracted. But the point is this conventional AC magnetometry, this is the AC gradiometry. If you look at the phase accumulated by this measurement, there's like a 5 times enhancement in the signal. And this is a simulation. This method is not going to work for all the case, but in certain case where the current flow very narrow channel, like an edge current in let's say transport device, there's a very high gradient, field gradient, then our method can give several order of magnitude enhancement in AC field sensitivity. So this method not going to work all the sample, going to work where the current flow is very narrow channel, especially like for instance, edge of the transport devices. Okay. As I promised, I'm going to speed up my talk. So I'm going to move to the next topic, which is, yeah.
the previous statement you're making that it only works for the with current density in the sum of the edges kind of large is because you need a kind of some sort of nonlinearity somewhere to have the distinct.
Yeah. So the basically the improvement in S1 comes from two factors. The denominator has the difference between frequency of AC current and the frequency of our tuning fork oscillating frequency.
Yeah.
So the bandwidth is very narrow, only work at certain frequency. And then the second factor for the enhancement is how large the field gradient. If sample is flat, the magnetic field is flat, then this is not going to work. There should be strong field gradient. Then our method will show the large enhancement. That's why here we basically do the simulation based on width and gap. So if you have a very narrow current flow, then our method gives significant enhancement. So not going to apply for any other sample, every sample, certain sample, especially transfer devices. So we like to apply this to the graphene device with the narrow channel and then demonstrate the strong enhancement in AC field. Okay, so the second part is a Y field. No scanning, just CCD camera and so on, and all optics. This is the image of our setup. And this transparent square is our diamond sample. So if you come to our lab, one of our shell, there's many this diamond plate, hundreds of them. It'll be how much will it be? 100 million USD, more than that. So you can come, you can visit our lab, you can do that. But you cannot resell because this looks very much same as just a broken piece of cover glass. Anyway, so this ESL is 3,000 USD to 10,000 USD, depending on the quality of guidance and anyway, so the idea is this. Now we have multiple epicenter, not single epi. We excite them all together and collect their fluorescence signal with this camera. So each pixel, there's epicenter located and detect local magnetic field. And then we can get this image. So this is optical image of ion magnetic nanowire. And this is a magnetic image of the nanowire, and this is simulation. I don't want to go detail, but white and black and white. So the pole of magnetic field reversed. So this is north pole, this is the south pole. And since we use multiple epicenter, there are 4 different directions of epicenter quantization axis, which means we can detect magnetic field along 4 different directions. If you analyze them all together, you can basically realize vector magnetometry. You have information about magnitude as well as direction of magnetic field from your target sample. So using this technique, people study various different condensed matter system. Spatial resolution is a micrometer, not nanometer. An image over large area. So this is the image of vortex from spot-conducting sample, and this is the image of current density from larger scale graphene devices. As you can see, the current density is higher at the corner or around some damaged area. So this technique, recently people try to use this to more likely real world application, industrial application. So Harvard group and then Europe, Germany, they put the diamond on the integrated circuit devices. And this is basically magnetic field images overlaid with optical image of circuit. So optically, it's hard to know which wire is broken, which wire is damaged. But if the wire is damaged, basically there's some discontinuity in terms of magnetic field. By measuring magnetic field, you can check, non-invasively check whether the wire is disconnected or not. So, and people extend to the more deeper layer devices, semiconductor devices. Okay, so recently, as I showed, we image magnetic field from individual magnetic nanowire. This is optical image, and these are all magnetic image with a different external magnetic field. It looks very complicated, but if you carefully analyze the image, this is north or south pole, but this reverse south north. And in the intermediate magnetic field, there's some two different domains. By carefully imaging this, we can extract the magnetic hysteresis loop from individual magnetic nanowire at room temperature and ambient. Very, very handy. So if the wire consists of magnetic, non-magnetic material or consists of two different magnetic material, from optical image, hard to identify, characterize them, but from magnetic image, we can basically extract their coercivity or saturation magnetization and so on from the magnetic image. I will give you one more example. Recently, we did magnetic steganography. So for those who are not familiar with the steganography, it's a technique of cryptography. Not quantum, it's very classical, has been used from ancient Greek. So basically the idea is you hide your message, you basically cover fake message and then hide your message. So in ancient Greek, people shave slaves' head and tattoo message. And then the message will be hidden, concealed when the hair is grown, and then send the slave to the recipient, and then recipient shave again to see the hidden message. That's the idea. So in our case, we hide diamond image under heart image. So there's a reason. This was done by our graduate student who already graduated. He did this before his marriage. So I guess he used this as a marriage proposal. He showed his heart as well as diamonds for proposal, wedding proposal. Anyway, so it was fun. We like to go further. Let's hide some information, not quantum, but classical. So we made two different barcodes, optically identical, but magnetically different. So this, if you do this, this is MD, this is the Korea KR. We extend this to further to the two-dimensional, which is a QR code, optically very similar, but magnetically very different image. And this goes to our group homepage, and this goes to the Korea University homepage. There's some quantum technique. I don't want to go in detail. To using Qtreat, not qubit, Qtreat state, then you can enhance sensitivity. So same quality, if you use Qtreat, there's some speed up of imaging time by 3 times. Anyway, so you can utilize quantum technique to do this. So I'm going to move to the final topic, which is the most important topic, I guess. Potential collaboration between Korea University and the center. So, and the strong point of the epicenter is you can sense magnetic field or other physical quantity at the nanometer scale. So this is one example from the looking group at Harvard. Basically, you study transfer dynamics, non-nuclear dynamics in graphene and other two-dimensional material by locally measured using epicenter. This can be, it's not imaging, but can do this kind of thing. And also, as I showed before, a 2D material that has an interesting magnetic property or other interesting property measurable by our technique and can realize nanometer scale characterization of this material. And also, this is done by Jacobi group at Harvard. We also have some Josephson diode image, Josephson diode effect using this scanning probe microscope technique. And by analyzing magnetic field and realize current density map, we can study various interesting phenomena in this device. this is not imaging technique, but this is the advantage of diamond. So people use diamond and build to pressurize sample, such as superconductor or some ferromagnetic material. But if you have a diamond in the center, at the end of this anvil, you can basically detect local magnetic field or temperature as a function of pressure. So this also how Norman Yao group. There's some controversy of this high dry superconductor, whether superconductor or not. So how they did is by changing pressure and temperature and measure Meissner effect. If it's indeed superconductor, there should be Meissner effect. By measuring magnetic field, low and above TC with a different pressure condition, they were able to confirm that this is indeed a superconductor. There are other groups. So recently, this is very hot field in condensed matter. Applying high pressure and varying temperature and locally measure magnetic field from superconductor or magnetic sample. And
Where could it be the optical channel and the microwave channel can go through with that system?
I'm sorry, what?
So where the optical window is
On the top or bottom?
just
Yeah, the size is just this. So
microwave, you also need to.
Yeah, you have to put microwave coil here. You have to do some patterning. So our group is need to initiate collaboration with Professor Kim at postdoc. So our initial preliminary data, this was all doable. And the sample can be extended to a two-dimensional material. I think I wrote this example. This is a two-dimensional material under high pressure. Okay, so there can be multiple topics. And I want to mention that the quantum sensor could be emerging tool to study quantum materials, including 2D materials. Okay, did I keep my promise? So this is I want to thank our group members and domestic and international collaborator and then funding support. Thank you for your attention.
For your lesson, do you have any question?
So the one essential part of doing this one in the wider range of the calculation tool is whether you can put either single MB or not single MB into the cryostats such that you can control the temperature,
Right.
hopefully down to say Kelvinish, and also kind of control the magnetic field more quantitatively, such that using the spectrum magnets and so on. I know that it's possible.
Yeah.
It becomes more expensive and kind of requires some planning.
Right.
But there's some plan for that.
Yeah, we have a cryostat in our lab. So only go down to several Kelvin because optical cryostat, and we have a 3-axis superconducting foil. Yeah, so the magnetic field can only go to 1,000 Gauss. But other group, they use more like a millikelvin cryostat with a superconductor magnet, so they can apply Tesla and go down to millikelvin range. And those cryogenic scanning tool is commercially available.
Oh, is that right?
Yeah, there are two companies that provide a commercial scanning tool. There are two companies in Switzerland, and one of them, they already sold one cryostat imaging the system to the one group in US. I forgot the group. Yeah.
What is the price range of those classes? Half million.
More than that. It's quite expensive. I don't know why. Probably they sell because it's combined quantum technique, cryostat, and so on. So there should be optics. Not only just the cryostat, optics should be integrated to low temperature. So quite expensive. So and many people they build their own apparatus.
Any other questions? what's the best resolution of detecting malign field
I mean, spatial resolution.
in your
Our lab, potentially 10 nanometer. We usually do 20 nanometer. So what the 10 nanometer is basically the MB center is located 10 nanometer from the surface of the scanning probe, diamond surface. If it's too close, then there's some issue of the property of the qubit. So typically 10 nanometer. So yeah, you can realize 10 nanometer once you touch your sample and image. But we don't want to do that. We don't want to damage our sample. So usually keep distance 10 nanometer away. So the resolution is, the smallest resolution we usually do is 20 nanometer.
Okay, thank you for your attention.
Thank you.